Hi, everyone. It's my pleasure to introduce Nasrin Mostafazadeh, and really needs no introduction because Nasrin has stayed with us here and done three consecutive internships. But just briefly, she's a graduate student at University of Rochester, about to graduate. She's currently in the Conversational Interaction and Spoken Dialogue group at the University of Rochester. We've worked together on question generation, so generating questions, not answering questions. And I trust that you'll talk about that,
Yeah, totally.
as well as the Rochester short stories corpus that kind of had its ideas came about here and discussions with Pushmeet and myself, but then you went back to Rochester and did great things with it. So looking forward to hearing it. Thank you.
Right. Thanks a lot for the nice introduction, Lucy. Thanks everyone for coming. It's kind of a late time. I didn't expect any of you to show up, but I'll try my best to keep it upbeat. And whenever I saw anyone falling asleep, like Chris, right there, I'm joking. I'll make sure to just ping me, ask me questions so that we can make it be dynamic. So it's really great to be back. I'm going to present today my ongoing research in the past 2 years or so on modeling context in eventful human-machine communications. And this is a joint work with so many great people, like my advisor, James Allen, and Lucy, my mentor here, including so many other great MSR people like Pushmeet and Chris Brockett, Bill Dolan, Michelle Galley, Xiao Dong, and Jian Feng, who's not here. So I'm really excited to share my ongoing research on this, but a lot of it has been shared with MSR folks, so you have to like it anyways. So human-level understanding and context is what I'm going to talk about today. So let's take a look a little bit on what I mean by context and why it's a challenging problem. So when we change the context for a very basic even language utterance like black beans, question mark, things change. So let's look at this one example. So the context is at grocery store. Let's say a customer asks the clerk black beans, meaning where are the black beans? And the clerk comes back saying aisle 3. So another example, imagine the context is back from grocery store. So the woman asks the man black beans, and the man replies, oh, sorry, forgot to get them. And as you see, the context is the natural language part is still consistent among these. And the third context is it's like in a serving food scenario. The woman asks black beans, and the man replies, yeah, love it. So this is like you can imagine what the context has been here. Like she's preparing food and is wondering. So that black beans question mark in that context just happens to mean do you want black beans on your food? And as humans, we do this wonderful job on inferring what everything means in context so wonderfully, and it's you can see how super challenging it is. And then if the role of the man and woman is reversed in this scenario, and the man says black beans, and the woman can say, oh, you don't like it? So that's interesting how so intonation and everything, right? It's like this real complex system of things that together add a meaning to what a context is. So fully understanding the underlying context for our daily conversations and human communications requires integration of agents, many things like perception, say speech, text, vision, which should be embedded with this word model, like sets of beliefs and desires, and dynamics of events, planning, and intention recognition. So it's a really complex set of things. And as a research community, we should explore all these and work on all of these. But of course, we choose to, slice and dice it into different kinds of projects and focus on some very narrow, narrower aspects of this actual real-world problem and reasoning. So let's take a look at an example of, Cortana understanding the language in context. So imagine it's only about language, right? Just setting aside all these other complexities that the real world, communication can have. So I asked Cortana, when did Albert Einstein die? And of course, it knows the answer and comes back with the date. And then I follow up, how did that happen? And of course, it has no idea what I mean. It just goes off and searches Bing for that. And just imagine maybe that's a hard utterance. So I change it to what caused the death. still it has no idea that the context was what I had asked about Albert Einstein's did, or what caused him to die, so doesn't work. And then, of course, if I directly ask what caused Albert Einstein to die, it will bring up the knowledge base retrieval for me, so which means obviously retrieving answers from a structured knowledge base is working kind of, these days very nicely and with kind of a good accuracy, but responding to open-ended utterances which require some sort of understanding in context is not doing a good job. And I know that Cortana would do a good job for a few select examples, like, if you ask about the president of the United States and follow up about the spouse, it will actually understand that. But beyond that, it's lacking. So my own ultimate research goal is to build systems which can collaborate with humans in creating contextually meaningful and coherent communications, with the ultimate goal of those systems being able to explain themselves. So this is just the research agenda. And this talk in particular is going to be on modeling human-machine communications around events, with a focus on common sense reasoning and contextual modeling. So I've spent a lot of time, my grad school and also undergrad, working on events. And why do I work on events? Why events matter? Just basically our world is filled with events, with things that happen. So what did happen here? What caused that fire and what's happening next? What did cause that, that collapse? Is that an earthquake? What is going to happen to all the, people who might be under it? Or like, how did he fall? What, did he break a leg? And why are they celebrating? What has happened? And so many different things that are like, what did happen here? No one knows. Why are everyone at the airports like with those signs? And what are they doing? So our world and the changes of our world are caused by the effects of events, and understanding events through either language or vision, which is something that I am exploring for predicting what happens next, is a very demanding area in AI, which is why I'm working on events. So this talk is going to have 3 case studies on modeling human-machine communications around events. The first one is going to be on textual narrative context. The second one is only on visual context. And the third one is on visual and textual context together. So let's dive into the very first one. This is modeling a textual narrative context, where the goal is to build a system that can understand and collaboratively compose stories with humans. So why do we care about story generation and story understanding in general? It's an extremely challenging task in NLP. It has been for a long time. Since like 70s, people have been trying to build systems that can tell us the stories, and they often classically looked at it as an AI planning problem. But perhaps the biggest challenge to story understanding is common sense knowledge, and having a way of interpreting like events and the sequence of events by having common sense knowledge. So again, like classically, the way of acquiring this kind of a common sense knowledge has been scripts or narrative structures, where you have these sets of stereotypical event sequences that co-occur together. So like this is something that my system will learn, that when an agent, which happens that this is a person, it wakes up, it will work out perhaps, and then it will eat something like a breakfast. So that's what a script is. So it really matters to define what I mean by a story here, because a story is this kind of an interdisciplinary thing that many people in AI, or even across like in psycholinguistics or psychology, cognitive science, work on. And so here today, in my current research, for me, a narrative or a story is anything which is told in the form of a causally or logically linked set of events. And that means that at the moment, I'm not concerned with how entertaining or dramatic stories are, or how the plots are, evolving and stuff like that, because I'm interested in the core causality links and how a logical story is being told. So the question is where to start learning stories or narrative structures from, after all. And, of course, you can start with reading newswires and personal web blog stories and etc., which is what we did. But there are 2 major problems. One, there's not much common sense knowledge if you try to scrape just newswires. And if you go with the personal weblog stories and stuff like that, because they're noisy, it's really hard to tease out useful information out of what they have. So it's like research-wise, we tried all these and it failed. And then we came up with this corpus called Rocket Stories. So Rocket Stories is collection of high-quality short 5-sentence stories with their titles, authored by hundreds of crowd workers, and the 5-sentence restriction happened to work really nicely because it gives enough room to the story to be told, but at the same time, it doesn't give room to sidetracking to unimportant information. So that was our way of teasing out any relevant or like maybe artistic twists and stuff like that. And the characteristic is that this is a realistic set of stories, and they have a specific beginning and ending where something happens in between. And as I said, nothing irrelevant or redundant to the core story happens. And after we did this, just for getting our own sort of causally linked, sequence of events, because that was our goal and definition of story, it happens to really nicely correlate with what people traditionally have defined stories as. So there's a beginning, there's a middle, something happens, and an end, and there's always a climax where something, maybe a character is posed with a really obstacle and then has to overcome it. So the statistics is that we collected 100,000 stories with many workers participated who really love telling us stories. So let's quickly take a look at an example, which is titled A Friendly Game. So the story goes, Bill thought he was a great basketball player. He challenged Sam to a friendly game. He agreed. Sam started to practice really hard, and eventually Sam beat Bill by 40 points. So as you can imagine, this story has a lot of causality and like linked sets of events, from which maybe a system can learn the following chain, that when X, like a person, challenges Y, that enables Y to agree to play, and then that's before Y practices, and then before Y beats X. And so this schema is something that we develop here as one of the works that I did with Lucy on how to actually make sense of the relations between events. And if you look at the title engram distributions, it's clearly a set of really diverse stories. So people talk often about something new. They talk about a new job or a new phone or lost stuff. So lost phone or like Christmas and stuff like that. So it's also dependent on timelines when these were collected. So our very last round of data collection was around the presidential election in the US. So this is an example. Let's read it. So this is written by a worker. So Tom was a great speaker. He talked about hatred and xenophobia in front of large groups of people. People were really inspired by his speech. They decided to vote for him. In the election, Tom became the president of the United States. And then I refuse to tell you what our system will learn from that for later generations. Okay, so now a major research question is how to do automatic evaluation on story understanding. And the research lately had been really hindered by a lack of a proper evaluation framework for evaluating this specific task of like story understanding or generation. So our idea is a story close test. And the goal here is to design a new evaluation scheme, a schema for story understanding and narrative structure learning. And the task we're proposing is as follows. Given a context of 4 sentences, the system is tasked with predicting the ending to the story. And we collected the evaluation data set for this by crowdsourcing. So let's go through a quick example. So the context goes, Tom and Cheryl have been together for 2 years. One day they went to a carnival together. He won her several stuffed bears and bought her funnel cakes. When they reached the Ferris wheel, he got down on one knee. So anyone, what would be an ending, a logical ending to this story? She said yes. Yeah, he proposed and she said yes. Perfect. So the right ending written by 2 different workers is, yeah, he proposed to Cheryl and she said yes, and Tom asked Cheryl to marry him. And notice that actually the notion of him proposing is not set in the text yet. And then 2 wrong endings by workers can be he wiped mud off of his boot, or Tom tied his shoe and left Cheryl, right? So in this is a funny example, which is why I put it there. You can somehow sort of imagine that can happen, like the wrong ending. But our data set is our data set of 3,744 doubly human verified instances make sure to include only cases on which humans agree. So there are no boundary cases. So let's take a look at a few models we developed for this task. So the first model is called learning type narrative schemas specifically. So this is a knowledge acquisition method. It's an unsupervised method to learn a narrative correlation of events. So on a large collection of documents, we start first running a dependency parser to extract so-called event slots, which is basically just pairs of events together with their subject or object roles. And then we run a co-reference resolver to find the co-reference chains, and co-reference chains are just a set of links, like, in the story about Bill, we had mentions of he, and all these will be chained together just so we know that they're referring back to Bill. And then we measure relatedness of each pair of event slots that share an argument, and then in an unsupervised way, we cluster the event slots using that measure of relatedness. So very quickly, this is how we try to learn the narrative structures for that specific story of Bill challenging Sam to a game. This can be a kind of a representation for it. So each entity would have its own, these colors present a type of a person, and that happens to be game. And we want to just maximize the score that we get from each narrative structure by some notion of similarity. So here, narrative similarity for each narrative structure and its event is defined by maximizing the chain similarity. So each of these is making a chain. And then at the end of the day, the similarity between each pair of events is defined by its just basic PMI, pointwise mutual information. So we trained this model on...
So the schema, again, is just a set of actions?
Each schema, yes. So each schema technically is just a set of, a sequence of shared co-occurring events, sets of events, exactly. And then they can be also temporally ordered, but for this task, we didn't want to care about temporal ordering. So classically, people would also add a temporal classifier so that they know what happens before what. Yes.
And the idea is you cluster them, you give some specified number of clusters you want them clustered to?
Yes, exactly. It's just basic unsupervised way of clustering co-occurring things. So at the end of the day, you know that you've seen so many times that challenging, accepting, and playing against and beating is very common. So anyway, so we trained this model on 2 data sets, one on Associated Press portion of Gigawars, which is a large corpus of millions of data points, and also on our own ROC stories, which is just 100,000 stories. So at test time, what we do is that we are choosing the ending, which yields the higher total narrative similarity measure, as I said, for the resulting narrative structure. So here, imagine that one of the structures can end with beating, and one of the structures can end with loving, let's say, and then the system knows that it has seen this structure way more often than that one. So the second model that I'm going to talk about, very briefly mentioning, because it's, I think, very well known in the MSR audience. It's an MSR sentence-to-vec model, which was trained to project the 4-sentence context and the 5th sentence onto the same, semantic space. And so as a result, you train those 2 separate deep neural nets to jointly learn the embeddings. And then at the end of the day, you choose the ending which has the closest cosine similarity to the context. So we also tried a few baseline models. The first baseline model was frequency, in which we discard the context. We just wanted to make sure, whether or not this baseline works. So we choose the ending with the higher search engine hits for the frequency of the main event. So in this case, we wanted to make sure that, neither of the endings is just too obviously impossible that a search engine would even tell us. The second baseline is n-gram overlap, which chooses the ending with higher n-gram overlap with the context. So this kind of tries with specifically with a smoothed blue metric. So this baseline tries to find out if, by just word overlap, you can find which ending is correct. The third one is average word to vec, which is just basically a little bit better version of n-gram overlap that takes into account word to vec for finding similarity. So again, it chooses the ending with the closer average word to vec to the average word to vec of the 4-sentence context. And another one is a sentiment match. This model chooses the ending that matches the sentiment of the context specifically. which we call full sentiment, or the one that matches the sentiment, the average sentiment of all the 4 sentences all, bunched together. And this is supposed to somehow tell us whether or not sentiment is an important factor. And last but not least, it's the Skip Thoughts model, which is Toronto sentence-to-vec encoder. This is trained on large corpus on stories, novels, book corpus they call it. And then again, this is an embedding, so you choose the one ending that has the least cosine distance to the context.
So these models, the embeddings, word-to-vec and skip thoughts, are based on different corpora? They're trained on different
Yes, so the Skip Thought model here is specifically trained on novels. The average word-to-vec, that one, the Jensen one, is actually specifically trained on Google Newswire. So they're just different. And also this is a sentence level embedding. That's a word level embedding. So it's just kind of different flavors of embedding so that we get a sense of.
Presumably you tried other metrics than average, like max?
I think it's very and sure. So in NLP it's common to look at things as a bag of words. So the basic bag of words model for word-to-vec is to average all the word-to-vecs. But yeah. So you'll see that this actually average word-to-vecs happens to do a good job often for doing similarity, but they're dumb. There's no question that it's a very shallow way of representing a sequence of words, for sure. So, all right. So let's take a look at the results with accuracy basically being number of correct choices divided to number of all test cases. And so across the models, you can see that a constant choose first would be 51%, and a random being 50. Basically, so as you see, none of the models is doing that significantly better than random, except and human does 100%. That's a very important feature of this particular framework because it makes the benchmarking easier towards an end goal of reaching human performance. So in the narrative chain model that I just described, the one trained on stories actually is 49.4. And then the DSSM, which is our best model trained on the 100K stories, is doing 59.5. So clearly there's a wide gap between human performance and the best system result that we got. And this just showed us that there is a wide enough gap from the state-of-the-art to human performance to motivate further research on this topic. So we were quite excited first when we released this. So this task just happened to have a really nice reception in the field just because sort of it was the right time and right place to think about how to evaluate story understanding, and everyone was excited about narrative understanding and narrative structural learning at the time. And then it happened that it was also picked up by DARPA CWC program on this story composition track as their evaluation framework. So there were other teams who were also engaged in this task, which made it, the momentum even better and better. And I've been amazed by seeing all the various use cases that, people come to me and talk to me about what they're doing with this data, which amazes me. So first of all, of course, they're training models which understand or tell stories. And they also train generic language models because these are short stories, to the point, contentful, so they can learn, just train language models. They also have been, I've heard, evaluating children's intellectual disabilities, which is quite interesting. Turns out that there are kids who cannot logically follow a sequence of sentences, and at some certain age, it's really helpful to have such a way of evaluating their, intellectual stance. And then developing theories of what makes a sequence actually a story is something else that I've seen people working on. Like, what is it about these common everyday stories that makes people tell them as opposed to some other boring? Yes?
So what I want to do is try to ask the kid to run this test and check the performance.
No, that's a very good question. I want to know what the answer to that is as well. That would be really fantastic to have an actual age of do kids pass this at 5 or 4? I would imagine it's a lot. Well, it depends on the story, right? Maybe a 5-year-old doesn't know about marriage proposal, but some other thing in which is, a character gets, knocked down and then still stands up and continues to fight or stuff like that. That's something basic for kids.
tool for vocabulary? Is vocabulary part of intelligence, or in reasoning is actually heavily correlated to the vocabulary you know, or all this kind of stuff?
Yeah, exactly. That's a very good question, and good. I would love to know the answer to that. And maybe next, when I have, I have some freedom of doing that, I would love to do that in some child language acquisition lab or something like that, and many other things. And then the list of all the papers and resources so far on the Rock Stories project is there. And as Lucy mentioned, the nice thing is that this whole project started here by, I was working on narrative structural learning before, but then I was working with Pushmit over summer, and he mentioned to me how he's fascinated with like learning stories, like from children's storybooks, learning to tell stories, and then it just spanned off and it got into all these different branches of affecting the community. So that's really nice. And so the story close test is now on, we put it on CodaLab, but then for more than 5 months, there wasn't any significant progress because, this task seemed hard, requiring common sense knowledge and deep understanding. So the time was ripe for us to hold the first sure task on a story close test. So we organized an EA sale workshop with the story close as the share task. It was actually held yesterday, but I couldn't go because if I did, I would not be able to come back today here or at all. So 18 teams registered to participate, and 8 teams participated at the end. Like I think 10 people were just afraid to take a crack at it. And then we used the original story class test set that was already publicly available, so it wasn't the blind challenge. But at the time, we really wanted to build up momentum for making a new state of the art, so that people are not afraid to come and try it. And the participants were encouraged to use any training data of their choice. So the submitted approaches ranged from rule-based methods and different linear classifiers with modeling different discourse phenomena and end-to-end neural models and hybrid models. So if you take a look at the leaderboard on CodaLab, the baseline was this. This is Rock NLP, our baseline. And then the UW team established a new state-of-the-art, which is 75%. So that's a significant increase over the baseline. So what did they do? They trained a logistic regression classifier using 2 different sets of features. One of them is a LSTM language model, which is just modeling the probabilities of the entire context and then trying to see which ending goes with that. And then the second one, which is the surprisingly interesting finding, is a linguistic stylistic feature on how people are authoring each ending independent from the context. So that's super interesting that I'm not going to spend much time today on talking about that, but that just signals that although we spend so much time on this particular task that I was trying to push for to make sure the data quality is high, it doesn't, the shallow methods don't work out and stuff like that, there is still a data bias. That's like something that, the linguistic stylistic feature, you can say that naturally also happens, right? If you want to say something that doesn't go with something else. So just by the way, this stylistic feature includes the kind of features used in gender or age classification or authorship classification for native, non-native speakers. Yes.
Sorry, just to be clear. Is the correct and incorrect ending both written by the same person who wrote the
exactly.
story?
And we tried both. We tried first to have 2 different people writing it, but then they were 2 separate. It was too far away.
The style difference. The same person wrote it.
Yes.
But they wrote it differently.
Yes. So happens, for instance, that I was talking with Esha this morning, and happens that it looks like this has happened in other domains as well, in which when you want to just make up something, you use so many adjectives. So number of adjectives happens to be really high in the wrong endings as opposed to wrong endings. And who knew, right? And I'm so I'm happy that we didn't. So if then a number of annotated data for right and wrong ending was more than 3,000 or whatever that we have, people would have made this whatever super complex hierarchical memory network to say that this is doing an amazing job, but then then at the end we will find out that the whole memory network was just trying to figure out number of adjectives in it, in an ending. So I appreciate the fact that first of all we were careful with knowing how many annotated data we were providing, and second of all I really appreciate the community involvement and studying the data and coming up. So I was amazed that the person who pioneered this study had already papers on authorship style detection. So it's like someone with that expertise came and took a look. So that's nice. And just really quickly, some notable trends is that 6 out of 8 teams all use DNN and neural nets in one way or another. And they, again, 6 out of 8 use some pre-trained embeddings, which help. And then another 3 systems actually report on sentiment being an important factor, which we had kind of sort of ruled out. So that's juicy. But let me get a crack at this first example. So I'm going to give you 2 examples on our model complexity dilemma. You may recall in a few slides ago, I just presented our narrative, type narrative schema learning, which was doing 49.4%. One of the teams that participated in our challenge actually used basic PMI score for all the word pairs in the context. Way simpler than our very complicated model that learns these, and achieved 59.9. So again, this is probably in our paper if we had used that and not in place of the state-of-the-art model for the learning narrative structure learning, that would have been a problem. So that's the kind of a problem in the community that maybe although we were careful, you should push even more for trying out really basic baselines first, and also credit anyone who writes a paper or establishes a baseline on really super simple ideas. So the second one, which is super interesting, so for sentiment analysis, the sentiment match baseline that I told you about, we had used this Stanford Core NLP's recursive neural network sentiment analysis that was trained on 12,000 sentences, and it's supposed to be, it has deep learning, so it's it should work, right? And then happens one of the systems that this team, another team had used is called Vader, which is a rule-based sentiment analysis method that was doing 58.2% versus 49.2% that we got with that recursive neural net one. So again, second example of how you should go for some other similar, simple stuff that just happened to work, and why shouldn't we take a look? And it just happens that I personally was really ashamed that I didn't know what Vader even is until I saw it there, just because, I keep hearing that on the news, and I don't hear about that, which is rule-based. So now, given the narrative context from human, let's explore generation as opposed to classification. So in our task currently, on the story close test, the system still does 75, human does 100. There's still plenty of room, which is definitely common sense knowledge, requires common sense knowledge and all sorts of things. And definitely for the next round, we will keep making new benchmarks, new data sets for evaluation. So story close test as a classification task is still intact on its own, but given the problems that we do have for any classification task, that it kind of, at the end of the day, becomes a hacking, engineering kind of an effort. I like to explore generation. So the task here is that given a context of 4 sentences, the system wants to generate the ending. So a little pitch on language generation, just where we are standing right now, is that the RNN language models are performing really well on generating grammatical outputs these days. So they're really doing a good job on modeling local coherency. So you will get a really nice little sentence out of it. But then contextually, sound generation is still super challenging. And generation given a topic or a title or a word or two is way easier than generating a logically sound output given a non-trivial context. So again, the focus here is that if the context is eventful, if the context is long enough, is contentful enough, the generation is hard, and I'll show you. And also generating Shakespeare-like text or poetry is often less challenging than writing a contentful sequence of logically related sentences. So that's another thing to keep in mind, that's actually cool. You see again on news that people are oh, this model spits out Shakespeare, and that's cool and stuff. But is that pushing forward AI or not, is the question that we should answer in the community. So here I'm gonna explore a basic sequence-to-sequence generation model, an encoder-decoder model with 2 layers, 500 12 units per layer, and a basic beam search with beam width 25 for generating the last ending. So let's take a look. I'm going to say that it's easy to generate something that kind of sort of makes sense if you discard the bigger context. So here what I'm going to do is to feed in the sequence-to-sequence model only the fourth sentence, so as opposed to the fuller context. So let's read this together. She wrote another through self-publishing avenues. So as humans, we have this incredible capability of filling in the blank, right? So when I read that, what do I think? Oh, like there was an author, and then, you know, she wrote something through self-publishing avenues. So the system given that generates, and they laughed, right? So you kind of can imagine that goes, right? That goes with that fourth sentence. So another example, she got it painted a bright pink color. So like there's a person, whatever name, got something painted a pink color. Kelly is very happy, right? You can always say that. It will go with it. And the name could be totally Kelly, right? And he did extra credit assignment, goes, everyone loved. And at midnight, he looked back and saw Anita dancing with another guy. And system goes, he was thrilled when he was the man he wanted to be. Right? These all go, right? It's like, and a bunch of other examples. So, but the important thing is to model context that is longer, and we need to do a better job on modeling longer context. So when I try the same sequence-to-sequence model on a full context, which is 4 sentences, it generates totally irrelevant things. But as you saw, I could totally get away with generating only using the 5th sentence, which is why it matters, to go beyond. So we tried this model, in which we are actually modifying the context to only retain main events. So we are using like a trip semantic parser here just to give us the main events and their semantic roles. But what that basically means is just that we are gonna this externally tell the system to ignore a few words that another external module is telling us is not important enough. So we thought that should, help the generation at least, because these kinds of methods are very data hungry and this is a super hard task. So let's see what happens. So an example generation context is John spends $20 a day on pickles. He decides to make his own to save money. He puts the pickles in brine and waits 2 weeks for his pickles to get sour. So the first generation is now he's so happy that he has money, and the second one is John opens the jar to find perfect pickles. So which one do you think is generated by machine and which one is human? How many people think the first one is by machine? Okay, good. Then you're right. So how could you tell? So anyone tell me, why did you know that was the system? The story is because, but he can be happy that he saved money, right? So it kind of still goes with the context, but it's super safe. It's obviously safe, and it's obvious that the system is just learning to say everything is good and happy and just predicting the sentiment of the ending. And the same example, another example is Carl lost her dog yesterday. She freaked out. Frantic Carl looked all over the town for it, and finally she found the dog in her neighbor's yard. Then in that case, she was relieved to have it back home as one of the generations. And the second one is she asked the neighbors not to put out treats. Which one in this case you think is the human? So how many think first one is machine? Okay, I like how one hand goes up and there are a few other brave people. Yeah, you're right. So again, it's like safe choices, right? Obviously safe language, safe set of events, and it's just very generic. So as you see, we are very much far from getting generations that are meaningful, that are that contentful. But even if I show you the bigger, so I could have stopped there, imagining that, we're kind of...
What's wrong with that generation or the previous one?
So nothing is...
Sensible.
Sure. Exactly. So I could have stopped showing you the generations at that point, and you would have left the room thinking that we are doing a wonderful job on generation. But more often this happens. Ivy wanted a cell phone like all her friends. She saved up her money from delivering papers, so soon she had enough phone, and then the system she was so happy she got on her food. So more often the generations are pretty much nonsensical. That's just irrelevant, right? Totally. Also agrammatical, totally. So that's my point, that actually still the system generation is not val. And if we cherry pick, and this one, yeah, Matthew read this. What was this about? Nicole wanted to be an ant more than anything, blah, blah. Anyway, he was glad he did not. And there's no he, really, or could be the husband, but doesn't go with the story. So anyways, my point is that we are so long, we are so beyond doing contentful generation with bigger context, and that just shows it. And so ongoing work, just to wrap up that part, is that we're working to learn to generalize way better, and any corpus for a generation task that requires common sense knowledge will be small for this kind of a task if we don't work on better abstractions. And one way of better abstraction that we are working on is to leverage semantic abstractions from other tools that can help us do a context representation. Absolutely.
They were both largely irrelevant, but also ungrammatical.
Right.
The grammaticality, why is that a problem?
Well, I think that what happens is that often it happens that you have to go down your beam search, like go down the list to pick up something that somehow is more diverse. So that's one thing we do in our re-ranking, and then that happens to be agrammatical, and that's what's happening in those generations. Okay, and the second thing we want to do for better narrative context representation is to learn to explain, which is something that we are doing, and we are calling explaining the explanation, the case of the story closeness, which I would be happy to talk about offline. And just a little pitch here is that I think the neural activation patterns are not how we explain as humans, and I think that we should explain through language, or at least there should be a joint effort between people who push for explaining through language itself. And also maybe sometimes when I ask a kid, why did you do this? You'll open the brain and see the neural activations. We can decide on them. So the second case study that I have is this work we did on modeling visual context, where the goal is to build a system that can ask a natural question given an eventful image as the context. So maybe too many people here have seen this photo before. Okay, I see too many faces, so I can't play my game. Anyways, I'll go ahead. I would have asked you, what do you think would be a natural question from that image? But then that's to spoil. So the amazing thing about that image is that it evokes this, this like next level of what we don't see in the photo. So you may ask, oh, like, is the motorcyclist all right? Which doesn't even exist in that photo. Or like the concept of injury and stuff like that, just by that image. So that's fascinating. That was the fascinating research problem that we wanted to work on. And we call this visual question generation, which goes beyond literal description of images. So the task definition is as follows. Given an image, an intelligent agent is supposed to ask a natural question in order to engage a user in a meaningful conversation. So for instance, for this image, asking who won the race is natural, but asking a VQA style visual question answering, which is a task you guys might be familiar with, like that, how many horses are in the field, is not natural. So we are shooting for that. And just very quickly, we think that VQA includes questions that are answerable by only looking at the image, and our intersection with that ideally would be minimal because it won't be natural to ask such a question. So really quickly, we created a data set for this, of course. We crowdsourced 3 different data sets, VQG Coco, Flickr, and Bing, totaling 15,000 data points, each 5 captions, 5 questions. So for VQG Bing, which is the thing I'm going to highlight, we queried Bing images for 1,200 eventful query terms to get eventful images. So that's the focus and the main, kind of a contribution of this work. So data characteristics, that we show that VQG actually evokes more abstract terms like think, like, feel and stuff like that. So that's obvious that it goes beyond literal. And another interesting observation is that if we, compute a textual similarity score among the 5 annotations on our dataset and other datasets, it shows that textual similarity is higher in VQG, meaning that there is more consensus about what is natural to ask rather than the other tasks. So we want to build a model that, given that image, will generate us what is being burned here. And we tried the retrieval model, which I'll just pass here. again, it just retrieves a candidate pool of k nearest neighbors and ranks them according to textual similarity to the pool. So our generation models, we tried 3 different generation models, but the successful one was a sequence-to-sequence GRN captioning model that gets in the, so that's on the right-hand side, that's the model I'm talking about. Given the input image, very classically, it transforms it into, using a CNN, gets the FC7 vector back, and then that would be fed into the RNN, which is we have GRU cells here to generate the actual, question. And vocabulary size, these details doesn't matter right now. And as I said, we tried 2 other models which were not successful in this task. So looking at the evaluation results, specifically human evaluation results, what we did was to ask 3 workers to judge the quality of a given question, a generated question given an image on a scale of 1 to 3. And as you can see, human also isn't doing a perfect job, but it's relatively high. These are out of 3. And happens that human consensus, which is something that is the most similar to the rest of the annotations, is doing better than picking one random. So that's the kind of a threshold to reach for a system. And our best system, our best system overall has, if we take the Bing data set as our major data set that we want to benchmark on, was the GRNN, which used all the training data. And as you see, there's a wide enough gap between human and machine performance to make further progress on in the community. And we also showed that there is a correlation, pretty high correlation between human evaluation and the blue or delta blue metrics. So we are encouraging the community to use those for benchmarking as well. So let's take a look at a few generations, example generations. So given this image of obviously some sort of an earthquake or something happening, the human would ask what caused the damage to the city. And our GRNN model would ask what happened to the city, or KNN would ask what state was this earthquake in. And the caption bot, Microsoft's caption bot, would caption it a pile of dirt. So another example quickly, the car crash, obviously. The GRNN would say, how did the car crash? And KNN would say, was anybody hurt in this accident? And then the caption bot would say, a man is standing next to a motorcycle. And I did try, these are what we reported in the paper, but I tried the caption bot last night as well, just to make sure this is still the case. So what happened, one of the interesting things we showed in this work in our paper was that when you go out of the scope of the training data, which is not only about captioning, but pretty much many AI tasks these days, the systems fail. So on our Bing dataset, which is a collection of eventful images, we show that Microsoft's caption bot does it's blue metric wise, it's 0.1. Although on MS Coco, which is a dataset that was trained on mainly, it's doing almost 0.3. So that's an interesting, finding, because these systems are really lacking in generalization. So if I input this to the caption bot, it comes back saying, I think it's a large elephant, which is true, right? But then that's a big red umbrella event, at least mention it, right? But why can't it do anything? Because it has never, ever seen that combination before. And it's not just the, captioning bot, our system as well. I just input this, it's asked, what kind of animal is this? As if there is nothing else wrong or absurd about this image. So we definitely need to work on somehow making our systems go beyond what they're trained on. So that's just a basic problem across tasks. So why learn even to ask questions, right? I just talked about asking questions for maybe 10 minutes. So asking the right question demonstrates intelligence, that's for sure. And then asking questions, we think, should be an integral component for any conversational agent, because you can proactively start a conversation by asking a question, right? The machine doesn't have to be always the one at the background that can be only asked for, service. It can engage the user. And also, it can elicit specific information per task. So this brings me to my very last case study. And if you are already tired, which you should be, it's 4:30, bear with me, this is the very last piece. And you'll see yet another task which models context. So in this task, which I'll go a tiny bit quicker over, the goal is to build a system that can engage in a natural conversation about eventful images. So in this case, the context is not only the image, but also the text. So let's assume this scenario. So this is Cortana. Imagine that one day a user can come in and say, hey, Cortana, look, my son is ahead and surprised, right? And then Cortana would come back, did he end up winning the race? And then this user says, yes, he won, he can't believe it. So you can totally imagine that this is a chit-chat scenario, but this kind of an engagement, contentful engagement with the user about like something that just happened to your kid can be really interesting add-on to any conversational agent. So we're introducing the task of image-grounded conversation, which, as it says, grounds conversation on images. And we are training this on millions of conversations around images on social media, which is out there, so we can use it. And IGC happens to sit in the continuum between chit-chat models and goal-directed conversational agents, because it's somehow this visual grounding somehow serves as a natural constraint to the topic of conversation. So it's not that the user comes in and says, hi, how are you doing? I'm good. How about you? How old are you? So it's contentful. That's what we are shooting for, and that's what the current conversational agents are lacking and need to improve on. And we also focus on questions and conversation openers. So the current scope of the task are 2 generation tasks. First, question generation, given the textual context and the image, and second, the response generation. So we are tackling 2 tasks. So let's quickly take a look at the data we use for training. This is Twitter data example. So it's like a crow. One user has said to the other, has tweeted this image along with that caption, I found a kawaii bird. And another user comes and comments, replies, are you going to collect some feathers? And the user says, there's so many crows here, I'd be surprised if I never found one. So it has some really interesting conversations, but at the same time it has some noise as well. So this is smile, why are you so obsessed with me? Oh, please. So obviously the system won't learn much from that data point. And of course at the moment it would be fantastic if our models could tease out noise from non-noise, but the models are not that powerful right now to be able to do that on their own. So this gave rise to us collecting our own crowd data for benchmarking the progress on this task, so that we know that the test data is at least a good one. And we actually did this crowdsourcing through work done at MSR by AJ and her collaborators, the CrowdChip tool. So we collected this data. This is an example for that eventful image. User 1 asked, a terrible storm destroys my house. And then the second user says, oh no, what are you going to do? And then the user comes back, I will go live with my dad until insurance company sorts it out. So the first context is going to be for question generation. So the context is going to be visual context and textual context. And the second task is response generation, which is given that image and those 2 utterances. So again, we are modeling multimodal context here. So just quickly going over data statistics, we trained on 250K Twitter conversations, and we collected 4,222 crowd conversations, which are eventful, contentful conversations. I'm gonna skip this effectiveness of multimodal context across the dataset, but just to quickly point out to the finding is that it's obvious that both modalities help. What happened? Okay. With my microphone, okay. Both modalities help the generation of the right question. So that's a task that's on question generation analysis. So we had a bunch of models for trying, to point out what happens when you do have visual context, but you don't have visual context or textual. So this is basically the same model we used for the VQG task. The second one is just a text-to-text empty, and the third one is both visual and context, but in this one, the textual context is just modeled as a bag of word models, which happens to, it has been shown to work really well in many vision and language tasks. And then the third model, the last model, is a visual and textual model, but this time we are encoding the textual context as an RNN. So let's look at a few generation examples. So this is a car which has been in a little accident. So a human comes and says, I got in a car wreck today. And then if the machine doesn't see that utterance and only looks at the image, it will ask, whose is that? Just again, very safe response, but just, you see a car and you ask, whose is that? But then if it does take into account the first user's utterance, it will ask what happened. So it clearly understands to a degree or correlates from data statistics that car wreck, and then that's this user's car, and you should follow up with what happened. And then the user can come back, oh, well, drunk driving. So this is an example of response generation. So the first user says, I got in a car wreck today, and then again, another input to the system would be another user's question, which is, did you get hurt? And then now we task the machine to generate us the next utterance, and the machine says, no, I'm home now. So it's clearly doing some sort of a good job in trying to model the context, but of course we are way behind what is ideal and what human is doing. So if you look at the human performance here, for Q is question generation and R is response generation. Human is doing around 2.6, and this is on our crowd IGC data set, test set. So human is doing around 2.6 and 2.7 on both Q and R generation, and our best model on which does across both models that we try with greedy search or beam search, it's clear that the visual and textual model, which is taking into account both modalities, is doing a better job. And again, there's a wide enough gap between whatever systems are doing and what human is doing for pushing the task, as a research forward with the community. So finally, conclusion. Well, congratulations, it's almost over. So just to conclude, we should model context effectively, and a stream of words is not good enough of a context representation. We can get away with that when we really have really short context, but then when we have bigger context, multimodal context, and we need better representations, and I think that we should, as a community, use what we already know about language and entities and maybe try to incorporate that somehow. And we need to work on marrying maybe semantic representations among other representation with generation techniques, and we need to somehow learn to generalize and make abstractions better than what we are right now. Thank you. Hey, any questions? Yes?
Are there any ways you could imagine representing out the context to people? It would be interesting to provide context for others.
So for people to do the task?
Well, I don't know. I think of if I joined an IM, a Twitter conversation, it would be interesting for me to not have to read the whole conversation, but have some of that context represented.
Right, so summarizing it somehow, because in Twitter, the conversation would be long, and yeah, that's an interesting thing to explore, but not directly relevant to what we are doing here. But definitely, a larger. I can totally imagine that one problem we have with these models, which are failing at context modeling, is to somehow, if there exists an oracle that summarizes it, push it through that, and then that get fed into our system. That totally would be something really interesting to explore. Hey, any other questions? Okay. Yeah.
The reason that I was finding the machine is because of our hypothesis that in the rock short stories, the ability to pick out which is the machine-generated one versus the human-generated one is that the machine. Again, it's our hypothesis that sentiment is usually there. So it was funny. He was relieved. She was, sad. There's usually some element of and that the machine is picking up on that.
Right, exactly. So you think that if you didn't know that ahead of time, maybe you would not have picked that?
Yeah.
Right. Yeah, I agree. There is
and I wonder if that's the linguistic, stylistic features are exactly that. There's some summarizing remark.
So that actually the sentiment part is shared between both wrong and right endings. So that's not a feature that is distinctively, about wrong or right ending. But what you said is right, that probably when we chose that one is because we know there is some sort of a sentiment factor that people have shown is effective in this task. And yeah, exactly. Yep.
On your conclusions, can you go back a slide? What do you mean by semantic?
Representation.
Marrying our semantic representations. So your conclusion is we need the semantic representations, but in the work you showed, you weren't doing that except in the first task, right?
Yes, exactly.
And then in the
You're not
first-
doing that in the two other tasks.
Right, so is this, you're basing this on the fact that there's still a gap and you're thinking the gap needs semantics?
Yeah, and I feel like I had this point in the narrative context modeling work that no matter how many data we collect, like now we have 100K stories, for the task that requires common sense knowledge, it's never going to be enough. And these systems need to make abstractions and generalizations. And I can't think of any better way right now to somehow give the system this heads up about generalization, but to use semantic representation. So when I use a semantic parser, let's say I can, replace the word apple with fruit, its type, or like kill with just an action that causes the like kill and like whatever cause to die mean the same thing, stuff like that. So that's some kind of, that's what I mean by semantic representation. And I think in many eventful context modelings that can be effective, but what I showed was just only in the case of a narrative context modeling, not the two other tasks.
I want this to be true, but I feel like the evidences keep fighting against it.
That's true. That
So
is
it's
true. But
disappointing.
that is true. But I think the evidences have not been on common sense reasoning and tasks which require really understanding the content of the context. But totally, I'm up for knowing which way to go by further explorations and studies. Yes.
I don't know really how to ask this question, so I'm going to try my best. So in one way, we are talking about common sense, which is such an abstract notion.
Totally.
I think as humans, we have some understanding of what common sense means. But in terms of testing how much the machine can capture this common sense, I feel like the evidence we have doesn't go beyond correlations, finding patterns in training data. And even if I see improving numbers in terms of like, yes, this response makes more sense than that, I don't know, like, I still get this dissatisfaction about, does the machine really learn common sense?
Yeah.
If I tweak the training data a little bit, or if I tweak the input image a little bit, if in the data I still don't find something that really like resembles this instance, like there is a nearest neighbor way, the machine still has no idea.
Right. Yeah.
So I just want to get your. I know this is such a hard topic. Nobody has the answer for this. But what are your thoughts about this gap between what humans understand as common sense and this kind of evolution?
Yeah. So that's, as you said, that's a major question. And what is even understanding, right? How can I show, like, can I choose a task that I somehow show that is foolproof and stuff like that? And then if a system does a good job on that, does it translate into it having common sense? Or maybe it's just, learning the characteristics of the specific training data that it's training on and correlations, as you said. And I think that it's hard, like maybe to a degree we should be fine with the fact that there's a benchmark and a system can beat the existing numbers and maybe it's doing something meaningful. But at the end of the day, I think as long as we keep testing our systems on different unbiased, like, unconstrained domains. So let's say, okay, now I'm building a chatbot, looks like it's doing something meaningful on my data, but let's deploy it in the real world with the real users and see how it's doing there. I think if we keep exposing our systems to real world, maybe we will get away, we will set aside the biases of the training data, and then maybe we can conclude that, well, if the system is really doing a good job in real human communications, maybe it's really having common sense. So, that's probably, But in short, I don't know. I don't know how best to make sure that, we keep making benchmarks. I'm on that same crowd, because we see the problems with the previous benchmarks, but then still we see problems with our own benchmarks. So what should we do and what are we even doing? And I think as long as we keep an open mind on the problems we face and the issues we have to address, we can make a meaningful progress as a community. towards maybe hopefully pushing for our agenda, which maybe, you know, for me happens to be common sense reasoning here. But then one other point I will add to that is that, so one of the shared task conclusions that we had, that, you know, 3 of the systems, as I said, had pointed out, was that sentiment analysis helps. So to me, at first, I would call it, that's too shallow. I don't want a system which models affection and, like, you know, emotions maybe to win this task. I'm in love with, you know, language understanding. I want common sense reasoning. But the truth is, tasks are so much multidimensional, and it's hard to tease apart different parts of intelligence, right? So I am also open-minded about, like right now, open-minded about what it means to have common sense knowledge. And maybe some things are not really that shallow. You know, I'm biased for thinking, say, sentiment analysis is shallow. So, yeah.
Hey, I was just going to say that common sense itself is contextual.
Yeah.
And sensitive to cultural expectations.
Totally, yeah.
Because what's common sense here is not common sense elsewhere.
Totally, so they're getting down
there's
on one knee example,
what-
perfect.
What is
Yeah.
common sense?
Exactly. Yeah. That's very controversial, totally. Okay, thank you everyone.
Thank you.
Thanks a lot.